Welcome to the fall edition of GEOTOP-A. Today we have Lisbeth Fajstrup, who's going to tell us about collapsing and directed topology. Take it away, Lisbeth.
Thank you, Louis. So thank you for letting me speak on this nice seminar. So what I'm going to tell you about is about collapsing, but not in the setting of directed topology, which is where I've been working for many years. And so the idea with collapsing is that you have a combinatorial space, which could be built of cubes or of simplices or whatnot, but a combinatorial space, and you want to simplify it. So for instance, you might want this pink cube here. If it's a full cube, you might want to say that you might as well have this one. I mean, and then the thing is, with might as well is debatable. What does that mean? So usually I would expect to have something with homotopy equivalences, but and spaces being homotopic. But I'm going to argue that this is not how it should work here in directed topology, mainly because you cannot do that. So that's what I'm going to tell you about today. And there are applications of these directed combinatorial spaces in concurrencies theory, and I'm not going to tell you anything about these applications today, so that will have to be at another time. So I'm going to go straight for this mathematical part with collapsing in directed topology. So what are my combinatorial or discrete spaces? They are Euclidean cubical complexes, and these are very simple things. So and I'm sticking to those because those are the ones where I can end up saying something in the end. So I have a union of elementary cubes, and an elementary cube in R3 is, for instance, it could be a 2 cube like this one, sort of a flat one. It could actually also be a 1 cube, so let me put an edge here. Or it could be a 3 cube like this one. So in general, it's a generalized interval like this from some vertex and then to this vertex plus a vector, which is a 0, 1 vector. So they can have, in Rn, they can have all dimensions up to n. And K0 I'm going to call the vertices. So these are my discrete spaces, and these are the ones I'm going to work with, and they are in Euclidean space, so no gluing relations coming from anywhere else. There are no loops, you could glue your way to a loop, but there are no directed loops. So it looks like this. So these are the ones I want to understand. And what I want to understand is, I want to understand this as a directed space. So you can imagine here that I would have x's. So let's just put them here. So here's an axis. Here's the first, and here's the second, and here's the third. So now I have put them in R3, which is what I have room for here. I could have directions on this. And the way I talk about directed spaces, or the way we talk about directed spaces, is we talk about the path spaces. So if I have such a cubical complex, Euclidean cubical complex, then I have a path to that subset of Rn, and then I require that if t is less than s in between 0 and 1, then for all coordinates I, gamma I of t should be less than or equal to gamma I of s. So I use the partial order on Rn to talk about that. And then the things we want to study are actually the spaces of directed directed paths. So you can think about this combinatorial structure, this Euclidean cubical complex, as sort of it is coding for a lot of these path spaces, and we give them the compact open topology because you do. So here's an example. So if my Euclidean cubical complex is the surface of the 3 cube, then the path space from here, so see I put arrows here to indicate the directions of the axis. So the path space from here to here, if it's the surface of the 3 cube, will be an S1. it's homotopy equivalent to an S1. Why is that? Well, I mean, paths can sort of go. If you draw like you'll get it's like putting paths on a sphere yeah, well, so you'll get an S1. But if you look at the path space from something like here, so this point to that point, then that will actually give you, there's one path here and there's one there, I mean up to reparametrization, so that will actually, the space will be two disjoint points. So this is very different from the from normal, you might say, or undirected topology, because your path spaces depend on the initial and final point here. And if you have the full 3-cube, then all path spaces are either just a point or they're empty, because you can always contract them. So now I want to collapse in this setting. So I want something with what happens to these directed path spaces, these spaces of directed paths here. And so here's a slightly more complicated Euclidean cubical complex. Someone taught me GeoTop-A. They should never have done that, because now I know how to do these things, these drawings here. So I want to say that, so let me remind you of collapsing in the non-directed sense. So I have a collapsing pair. So this could be a vertex, for instance, and a cube. And it's a collapsing pair in the non-direction sense if this sigma is a unique maximal cophase of this tau. So for instance, such a vertex like this purple one here is with the, so if this is tau, and then sigma could be this little square here, then this will be, this pair, tau comma sigma, will be a collapsing pair. And I can then, when I have a collapsing pair, I can remove the vertex, the edges, and the interior of sigma here. So I can sort of get down to just having this edge here left of that little square there. So that's what I would like to do in the directed sense. And when we do it in the non-directed setting, then what we get is that what we get after removing is something which is not only homotopy equivalent to what we had originally, but it's a deformation retract. So, which makes them very, very, very like each other. So the result of removing this stuff is a deformation retract of what I had before. So in this way, I'm simplifying what I had before, right? So let's look at this in the directed sense. So say we have here's a 3-cube, and it's the full 3-cube. And now I'm looking at this little vertex here, and I've also put directions on it. So I want to collapse that vertex. It's certainly it's a free vertex in the sense of the non-directed thing. Can I then collapse this 3-cube, full 3-cube, to these 3 faces here? That one, and the one in the back. Well, it's hard to see top and back. And my claim is that in a directed way, there's not even a retraction. So you want a deformation retract, so you want, but let's just look at the map you want in the end. So there's not even a map of directed spaces from the full cube here to the green part here, these 3 faces. And then we don't have to talk about what we would mean by a directed homotopy, because if there's no map, then there's no map. So why is there no map there? Well, so let me show you. Well, first I have to say what I mean by a directed map. And what is a map of directed spaces? Well, a map of directed spaces, DIMAP, nice name, is a continuous map, and it has to send path spaces to path spaces, or to subsets of path spaces. So if I have directed paths from x to y, then then using f on it, I get a new directed path just from f of x to f of y. Okay, and in particular, if I have paths from x to y, then there should be paths from f of x to f of y. So I'm going to denote that x is less than or equal with such a curly equality sign here to say that there's a path from x to y. So what I'm saying here is that if there's a path from x to y, then there should be a path from f of x to f of y. And every time I say path, I mean directed path. That's sort of, so yeah. So now using that, I'm going to say that I do not have even a directed map from this cube to what should be left there. So let's see. So this vertex, so these vertices, they have names. I mean, again, this is what GeoTop-A gives them. So I can observe that this vertex I have, and which at least I want to map that to the green part. This vertex it sits below. There's a path from this to that to F here. And there's a path from this one to where is it? There's a path from here to here, right? And this is a minimum, and this is a maximum of this in a directed sense of this. So there's a path from here to here. There's a path from here to here. So this means that if I take f of this, I have to hit a point from which there is a directed path in the green part to f and to C. And this means that I have to map to something that's below this and is in the green part. And what is that? That's this point. That's the only one that's below 110, which is this one, and 101, which is this one. Because, I mean, there is one below it, which was the one I had, but, I mean, this, I'm removing that part. So, okay, so f of my vertex I want to collapse is the initial here. Well, okay, that doesn't give me any problems. But now, what about this path that I had from here to there? Well, that's fine. That has to go to this, here and here, because it has to be directed and go from something where the second coordinate is 0 to something where the second coordinate is 0, so it has to stay with the second coordinate 0. So it goes there. Again, no problem. That's a nice path. But now we get problems, because a point like this, which is on that path before I do f to it, there's a path from here to, well, can I do this? To there. So that edge up there, I mean, before I map it. So this point is less than that one in the curly way. This means that from f of this, there has to be a path to this one, right? So this means that, and I know that this has to go to somewhere on these two edges. So it cannot go to this top edge, because then you are above this. So it has to go to here. And this is true for all points here, all the way up to until the very last one. It has to map to this edge. But I want a continuous path, so that's not going to, I mean, that's not going to fly. So I do not have a directed map that keeps the green stuff fixed. I mean, a retract, to say it in the right way. I cannot keep all the green points fixed and map and get a directed map from the 3 cube to that. So this sort of kills the idea that there should be a deformation retract, because there is no retract. So, well, okay. So what we learn from this is that we cannot take all directed paths into account here. And also, I mean, we're doing a combinatorial thing. So we're doing combinatorial spaces with a direction on them. So it's maybe natural that not all paths should be allowed or should be thought of. So the idea is now that we should instead also look at combinatorial models of the path spaces. And we should only look at paths that start in vertices. Because we're looking at a combinatorial thing, we're looking at discrete things, so we want some combinatorial models of the path spaces. And there are lots of those around. I mean, this is, for instance, Krzysztof Szymanski, it's Martin Rausen, it's Roy Schulam. There's several papers and there's several different models, and I'm not going to go too much into that. I'm just, I mean, I think that's, but there are lots of those. I'm not going to use any of them really seriously, but this is just the idea that we are only going for a combinatorial thing, so maybe not ask for every path, every continuous path. The reason why we can do it in the non-directed setting is that it works there. It doesn't matter, so we might as well. So I should perhaps say that something like this is also what makes it difficult to put model structures on directed spaces, or so. But I mean, don't ask me too much about that. I'm not very good with model structures. But anyway, so that gives you that because you want. I mean, you know, if you think about these inner Horn conditions and so on, you get in trouble with that as well. So, well, yeah. So I want to preserve path spaces from vertices to vertices, and I want to make sure that when I collapse stuff, these are preserved, right? So here's an example of, here's a heads up of something else, because so it's I mean, so you should think that there's a hole here. So this square is not filled in. So and I mean, there could be a lot of these squares in between. So maybe I want to say, okay, this one is a free edge, very nice. Can I collapse that into here? Well, if I look at the path space before collapse, then from here to there are two essentially different ways. There are two connected components of the path space, namely going below the hole and then going up to this V2, or going this way around and going up to this V2 and going maybe through some of this stuff that doesn't matter. So there are two connected components. If I collapse this sigma, then this way of going up to the top vertex is not there anymore because I removed all of this stuff. So there's some local to global thing that isn't working. Because here, I mean, locally it looks very fine. I mean, I collapse this thing, what's going on? I mean, no, not much, and no problem, should be no problems. But, well, there is a problem. So this global effect with the local condition is problematic and is difficult. So, yeah. So I read in the nice email from Jose Carlos that I should allow for some questions after about 20 minutes. I guess that's now. Any questions now? Yeah, I guess I can't see, so someone else should keep track of that. Maybe there aren't any. Okay, well, so yeah, no questions. Good. So let me think there aren't any. So this is just to line up why this is non-trivial. I mean, why the theorems we get look a little bit, well, I mean, can't they do better? Well, I mean, there's a reason. I mean, one reason is that it doesn't work. I mean, so here's the first theorem I want to present to you. It's a theorem that that is done with these. So I put the names vertically here. So it's me, and then it's Robin Belton, Robin Brooks, Stefania Ebley, Brittany Fassi, Nicole Sanderson, Elizabeth Vidore. And this is a WIT group, Women in Topology group, and we're having, I mean, it's good fun to work with all these young women. I mean, we're having a lot of fun. And we proved this. I mean, it was published this year, but as you know, I mean, this is probably because we proved it earlier. But anyway, so what did we prove? We proved that if we have, so first of all, we say something about the complex, or the Euclidean cubical complex. We say there is a minimal vertex. And with that, I mean there is a vertex from which everything else is reachable. So for that, I only have to say that all vertices are reachable. So this means that if I take some vertex in my complex K, then the path space from V to that vertex is non-empty. They're all reachable from there. So there's a minimal vertex. Okay, that's one condition. Then I'm saying, okay, I have a collapsing pair in the usual sense, and the minimum of of the smaller one is not the same. Well, the minimum of the two are not the same. So this means that if my sigma is, if we have the 2 cube and this is sigma, and it looks like this, then I'm allowed to do this tau, and I'm allowed to do this tau, and I'm allowed to do this tau. Now I have 3 taus. And I'm allowed to do something like this, and something like this, but not that one and that one, because the minimum of those are the same as the minimum of sigma. With that, so if I have that, and K prime is then the collapse, what I get after collapsing this thing, then the following holds. All path spaces from V, my minimum, to whatever, if they are all trivial before I collapse, then they're all trivial after I collapse, and vice versa. So, so what I'm saying here is that collapsing preserves triviality, and this is and again, remember, it's not easy, so that's why the theorem is not maybe not that impressive. And actually what I also know is that if they're all connected before, then they're all connected after, and vice versa. So there's a thing with connected. So it's contractible, and connected is everything contractible before means everything contractible after, and vice versa. And same thing with connected before. Everything connected before means everything connected after. And there should be, I should say, there should be a theorem saying something with everything K connected before is the same as everything K connected afterwards, but we didn't prove that. For that, you would need the K connected nerve limb and do some work, but we didn't do that work yet. So, we didn't do that work. So how would you prove a thing like that? Because, we know things are complicated because of this up here. Well, what we do is we use one of these combinatorial things. So Krzysztof Szymanski has the following, which is more or less using the nerve lemma. It says that if you take the path space from your initial point to, or from some point, and then I'm looking for the path space from V to some W. Then I look at the ones that are just below that W. So they get to W except for maybe a 0, 1 vector. So they get to W minus and then some 0, 1 vector. So right below. They get to the last cube before W, might say. If all these path spaces are contractible, the ones that get to just before W, then the path space to W is homotopy equivalent to the past link. Okay, so what's the past link? The past link is the set of all these 0, 1 vectors except for the one that's 0 everywhere, such that the cube between this go down by the 0, 1 vector and W is there. So for instance, if I go down from, if this is my W, if I go and we're in the plane, then if I go down with 1, 1, I get to here, and I want the whole cube here to be in K. So the set of all these, that gives me a simplicial complex that it's called the past link. And I have a drawing of one here as well, though this is where this is a minimal. So here is, well, that should be a W because V was the minimum, right? So I take the past link, and this is, so it's you could think about it that it's this edge, this face, this edge, and then this face on the other side, and then this edge over here. So you get 1, 2, 3 points, and they're connected by edges here. If this is what we have. So this is more or less the nerve lemma, or you could say it's something with a co-limit over this category, whatever you prefer. So this is what we use. And again, we do not provide any maps from K to K prime to the collapse complex. There are no directed maps. So one place where our theorem actually works is this one where we collapse the one I had before, and then I don't have this complication with this hole very far down. So everything is contractible. All path spaces are contractible before, and all path spaces are contractible after. So we're good. So the theorem works, but no maps. I mean, there are no directed maps. So now, so this is the theorem, and now I'm going to explain a little bit why it looks like it does and how we do it. So first of all, why do we need this this minimum, this minimal vertex or minimum vertex? Some American told me that it's a minimum vertex, or not a minimal. Well, okay, so it's a minimum. And why do we only guarantee anything in something about path spaces from this minimum vertex here? Well, so partial answer to this is that this condition with tau and sigma collapsing pair and the minimum of tau is not the same as the minimum of sigma. What this gives us is that if I have a vertex in K prime, then the past link of that vertex in K prime is homotopy equivalent to the past link of that vertex in the original K. So what we're going for here is for preserving past links. And this condition with that we just need that the minima are different is something we did in a paper in 2022. So it's a question, or the theorem goes via this thing with past links. So we're trying to, instead of thinking we preserve path spaces, we're preserving past links. So yeah. So what we know is that if we have, so now remember there was this thing that Siemianski had with the connection between past links and the homotopy type of the path spaces. So from that, it's not difficult to get that if we have for all vertices that the past link is contractible, then the path spaces are contractible for all vertices here. And why is that? Well, I mean, this is because this is an induction. You start from below, and then you use this thing that if every path space to right below my vertex is contractible, then the path space to the vertex I'm interested in is homotopy equivalent to the link, which is then contractible. So there you go. So that's kind of it's an induction over that. Yeah, and with connectedness, you have to be. I mean, you also have that. It's a slightly different proof. It has to do with something with a connected. What is it? The co-limit over connected spaces, where you take the co-limit over a connected category is connected. I mean, connected category meaning that the geometric realization is connected. So something like that. So let's look at the problem if we try to not take this minimum vertex. But this is now the surface of the 3 cube, and I've removed the top face. I mean, I do that. A lot of my examples are removing faces of the surface of the cube. So here it's the top face. So if you think a little bit about it, or look at it, all past links are in fact contractible. I mean, the past link of this thing is, for instance, that and that. So it's sort of 2 edges joined together there. Past link, yeah. So they are all contractible. The past link here, I mean, if you take the link, it's not contractible because you get a circle, but the past link is just this edge down here. So they are all contractible. Okay, so this means that if you take path spaces from V to whatever, you get a contractible path space. But what if instead I take a path space from here? So now take this vertex. Well, then I get this path and this path from here to there. And that's all I get, because remember, it has to be directed. So I'm not going to go down into the rest of this surface of a cube. There's no way I can do that. So this means that it's disjoint. It's not contractible. It's not even connected. So what's the problem here? Well, the problem is, you might say, that if we look at the link of W in the original space, we get what I showed before. We get a wedge like this. If we look at the link in what's interesting, namely the space between this V hat and this W, well, the space between this v hat and this w is this. So the past link of w is a point and a point. So there is this connection between, I mean, the space and what do we mean by a past link. And I mean, I could, of course, I mean, I could look at the past links with respect to some vertex, and that would probably give me, I mean, that's another way of formulating it. But this is why I don't get it for all initial vertices. So, well, okay. So that's yeah. So that's not going to work. The way you can think about this is that these past links can be thought about as obstructions in the usual algebraic topology sense. Because we know that if all past links are contractible, then all path spaces are contractible. We know that if all past links are connected, then all path spaces are connected. But if we want to go from path spaces in the original space to path spaces in the collapse space, then we have to have something about getting from path spaces to links, past links, then to past links because they were in the collapse space, and then to path spaces there. So I actually need to know that these obstructions are also realized, namely that there is an arrow in the other direction, that if the path spaces are contractible, then there is a, yeah. So I need to go in the other direction. So this is realizing the obstructions, in the sense that if there is a non-contractible past link, then I want to know there is a non-contractible path space, and similarly for disconnected past link, then there is a disconnected path space. And yes, we can actually do that. I'll get into that in a minute, but let me just show you how that actually gives me my theorem. So yeah. So now I have the tools, and I've repeated the theorem because otherwise I had to go back in my slides, which I've already written on, so that's not going to work. So this is the setup, right? I have a minimum vertex, I have a Euclidean cubical complex, I have a collapsing pair such that the minimum of tau is not the same as the minimum of sigma, meaning that past links in K and past links in K prime are homotopy equivalent. So now I want to say that if I have this property of all the path spaces, then in K, then I can get this property of all the path spaces in K prime and vice versa. So the idea will be to say, okay, this, to go one way, this implies that all past links, and then just go with contractible, so you can think connected if you want to. This implies all past links are contractible, so past links in K. And then I want to use this to say that all past links in K prime are contractible. And then I want to go like this, right? So for this is where I need my the realization result, that if they are all contractible, then all past links are also contractible. So there is a little thing here, because I'm only looking at the vertices that are also there in K prime. So let me face that first, because what about the vertices that are in K and not in K prime? Well, there cannot be a lot of those, because if you collapse, the only way of getting rid of a vertex is if the smaller of the collapsing pair is actually a vertex. And then the thing is, if that's a free vertex, then it's not so difficult to see that the past link, it's only going to be in sigma, the past link, and this it is contractible. So and then you go from that to see that that also the path spaces to this to tau are contractible and connected and whatever. So that's not a problem. I'm just saying that's not a problem, because when you know it's a collapsing pair, you have that. Okay. So now we know from, yeah, so this is more or less it. We know from yeah, so this is more or less the reasoning I gave up here, that you go from all path links contractible in one to all path links contractible in the other one, and back to all path spaces contractible. For connected, you have to be a little bit. I mean, you have to. The reasoning goes a little differently, because you don't have this thing with the nerve lemma. But then, as I said before, you do know that these you formulate this way, that this path space is a co-limit of all path spaces to just before, and the index category is, again, it's this category here, which is in fact the which gives you the path link if you geometrically realize it. And now if you take a co-limit of connected spaces over a connected category, it is connected. So this is what you use in that case, where you don't have Krzysztof Szymanski's result for the path links and collapsible. What? No. Contractible. That's what I was going to say. There are a lot of words here. So this is more. This is a proof of this theorem, and none of it is very deep. It's just that it's not. I mean, you have to realize that is non-trivial. I mean, that these directed spaces is non-trivial, because you think you can do it. Okay, I can do it the way I used to, and then you start looking for maps which aren't there, and that's going to take you a long time, right? So you can spend a lot of time looking for maps which aren't there. So yeah. So let me just show you. So what I wanted to also show you is this thing with how the realization of obstructions, which I actually think is kind of cool. So, and this is again work together with the wet group. So let's go for contractible first. So if I have a non-contractible path link, then there are two possibilities. Either one of the path spaces right below it, I mean, go down by one of these 0, 1 vectors, is not contractible, or if they are all contractible, then the link, then this path space is non-contractible, because then it's homotopy equivalent to the path link. And when I thought about that, I thought, well, I mean, it's going to be non-contractible, isn't it? I mean, we're going to have this anyway. This is not going to be necessary. But that's not true. I mean, you could have that this is not contractible, but the path space here is contractible, but something below is not contractible. So here's an example. So now it's the surface of the cube, and now, be careful, I've taken out the bottom of this thing. So, okay, so the path link here, that's an S1, because that's because it's the surface of the cube. So that's sort of like this, that goes like around like this. So that's this edges of the two simplex, or an S1. So non-contractible. But if you look at the path spaces the paths from here to there, I mean, they can all be, I mean, this is just they're all equivalent to just one path, because you can sort of move them all around like this. So that path space is actually contractible. It's just a point. But what is true is that if you look at this right below here, so go down by 0, 0, 1, which I think is correct if this is the third axis, then that is, as we had before, that is 2 points, because that's the one where you go around here and you go around here. So that's the path space here. So this is disconnected. This is even disconnected, but it's certainly not contractible. So that's because of this strange phenomenon you have, that these two paths, they are not, I mean, this is actually an example. These two paths are not directed homotopy equivalent. But if you then concatenate with this path, well, then they are, because then you're allowed to move all the way up here and all the way up to the other side. So that's another weird phenomenon in directed topology, which is then, I mean, seen here. So the obstructions are realized, but maybe not at this exact point. I could, of course, have said, let's this be a minimal vertex where this is not contractible, then I could have skipped, then I would have gotten it realized at this W. But just to say that you can have that and not and have contractible path spaces to there. But for connected, you actually get it realized always at the vertex. So say we have this path link that's disconnected, and I'm still in this setting with a minimum vertex. Then I claim the path space to that vertex is disconnected. And I show you a little bit of the proof because it's kind of, I like this proof. So let's take two vertices which are in different components of, because this was disconnected, so I can do that. So I do that, I've got this one, and I've got this one. They're in different components. And they are in the link, so this means that this edge is there. So this edge is there, and this edge is there, which is in, I guess, edge E2. These edges are there, right? Now this, because of this thing with the minimum, this is reachable from here, and this is also reachable from here. So here's a path to one of them, here's a path to the other one, right? So now I'm sure you realize what I'm trying to do. I claim that these mu1 and mu2, they're in different connected component of this thing. And how do you then realize that? I mean, the way you do it is, suppose they're not. Then there is a path from this path to this path in this path space, which said in another way is directed homotopy. So there is a family of paths here connecting these up. You can fill it out with a sort of two surface here. That immediately doesn't help you too much because you want a combinatorial version of this, because remember you want something to say that then these would be connected in the link, and that's a combinatorial thing. So what you have to do now is you use an old theorem of mine, which is why I like this. We have an old theorem which says that in this case, there's a combinatorial approximation of these two, which is have them run on the edges of this cubical complex. And for the homotopy, there's a combinatorial approximation of that, meaning that you have it running on the two skeleton of this Euclidean cubical complex. So you can do that, and that in the end it ends up giving you a connection between this J1 and J2 in this path link, which you couldn't have because they're in different components. So this is how you do that. So you get it realized at this point. But again, you do need to use, we use seriously that we have this minimum, and because otherwise lots of things can go wrong. If you don't have everything reachable from V, you cannot, lots of things can happen just in sort of in disguise, hidden from V. So yeah. So the conclusion, I'm getting to the conclusion, yay. The conclusion is that if we want to collapse directed Euclidean cubical complexes, then we need to analyze the path spaces before and after. We do not have a directed map which will then, on the space level, which will then induce maps on the path spaces. But we could perhaps, and that I don't know, but we could perhaps hope for such a collapse, inducing maps of one of the many combinatorial models of path spaces, that is, induce a combinatorial thing. Maybe we can do that, but we won't get it via a map like that because we don't, there isn't one, even in very simple. And I thought I had to go to dimension 4 for this to go wrong, but it goes wrong in dimension 3, which is, yeah. So I think this is the conclusion, that it's not easy, and there's work to be done, and that's of course a good thing. So yeah, I think I'll stop here.
Elizabeth, thank you for a very interesting talk. So how about some questions from the audience?
You have in mind applications for this?
I do, yeah. So
can you tell us something?
Yeah, well, can I reveal some of that? Yes, I can. And I've actually inserted stuff here, see? So we have this combinatorial, this directed topology originally, you might say, appeared because we needed it as a model for some problems in concurrency, which is parallel computing. So let me do the simple one that I can do. So it looks like this. So I have one, let's say a thread, because it's modern, so it's Java. So here's a thread. This is a thread. It wants to access a resource called A, wants to access a resource called B, wants to release this resource, and wants to release the other one. So this is thread number 1. Here's thread number 2. It does the other direction, and there's some reason why it does that. I mean, you can think about booking airline tickets or something like that. Lots of examples. This one accesses this resource, then access to that one, then release, and then release. And an execution of these, I mean, if you just do one of them, it's just, it's a graph, it's a very simple graph, but if you do one of them, you just have to run from here to here. If you do the other one, you run from here to here. So a joint execution is running from here to here, always increasing in both coordinates. So it's a directed path. Okay. But so how does that, that's not interesting because it's just, in the plane, we need some holes because it's topology. The thing is, these two resources, they only allow access by one thread at a time. So this means that while this guy has access to the resource A, the other one cannot get it. So this means that this whole thing cannot be accessed if you want to run from here to here in a joint execution. Same thing with this resource B. It cannot be accessed by two, hence they cannot both be there at the same time. So this tells me that to get from here to there, I want to follow a directed path, because an execution is a way of going from here to here and always increasing. And you might say, why would you want to do this in a continuous way? Because this is, don't they go in steps, these computers? Yes, that's true. But this is sort of a very bird's eye view of this computing. We don't know what it's doing meanwhile. It could do lots of stuff while it's in here. So there might be lots and lots and lots of steps along here. And you want also to have it being robust to subdivision, that it suddenly decides to do more things in here. So it's fair to model it with continuous paths. And there's another one going here, and up to equivalence of executions, which is fortunately the same as homotopy in a directed sense. There are only these two executions of this joint program. And you can imagine in higher dimensions you have resources that allow 2 and not 3 and so on, and you can get from that you can get lots of cool, interesting models or Euclidean cubical complexes. So that's one application, right?
Thank you.
You're welcome.
Lisbeth, collapsing was a very popular technique in the PL topology in the 60s.
Yeah.
With the work of Zeeman, Hudson, Licorice, and all those guys and gals. So, is any of that stuff from the past useful or interesting in the work you're doing?
Well, you can say that that what we're doing is sort of redoing all of that just in this directed topology, right? So there's a lot of, well, can we do it in that way? No, we cannot quite. We have to do something else because, there are many. So because of, for instance, we cannot collapses do not sort of happen on the. We cannot analyze them on the space level. We have to analyze the path space level, which is a totally different ballgame. And this, of course, has to do with the way that this is very sensitive to moving the initial points of these or the endpoints of these. So so that's one reason. So we try to redo it, and then I mean, we've done that to start with. We thought, okay, it's topology, but then, I mean, it's topology with quite a twist, you might say. But you're right. I mean, this is of course a discussion with PL compared to continuous. I mean, that's for sure. I mean, yeah.
The directed just makes things a lot harder to prove. Yeah.
Yeah, more fun. So, yeah, well, I mean, depending on what you think. No, I mean, so there are. I mean, we have many. There are many of these things around. I mean, if you look at the, well, I mean, the parameter spaces for multi-dimensional persistent homology and stuff like that. There are not lots of directed spaces if you start looking for them. You know, so yeah. I mean, there are the robot problems. I mean, robot problems as well. I mean, you can give them a time cone where there's some, maybe they don't turn as well, so you get the direction on those. So, yeah.
Very interesting. Yeah.
Thanks.
How about some other questions?
So who has questions?
Okay, well, if there are no questions, let's thank our speaker very much.